Hey everyone, so this is the next section in chapter P, the prerequisite chapter in pre-calculus. This section, P3, is all about radical and rational exponents, and these are the objectives that we are going to be discussing in this video. After this video, we're going to get a refresher, and this is what we should be able to do after watching this video. Evaluate radicals, add and subtract roots, use the product and quotient rules to simplify roots, rationalize denominators, and understand and use rational exponents. Okay, so that's our to-do list. If you can't do some of those things after watching this video, go back and rewatch it, look for more resources in the folder, send me a message, but this is what we should be able to do after this video. So let's get started here. And this is just a refresher on some things that really should be a good review. So square root of 64, hopefully we know that is 8. That's a perfect square. That's one that should be really fast. Number 2, a negative square root of 49. So square root of 49, we know that. That's going to be 7. And there's a negative in the front here, which is like multiplying this radical by negative 1. So our final answer is going to be negative 7. Number 3, square root of 1/4. We know that there's a quotient property. If I have the square root of a fraction, it's also equal to the square root of the numerator over the square root of the denominator. And this, now I know, square root of 1 is 1, square root of 4 is 2. Number 4, we have square root of 9 plus 16. We can add the inside here. So we're going to get square root of 25, which I know the square root of 25 is 5. And then number 5, this is different than 4. I can't combine these. I will simplify these radicals separately. So square root of 9 gives me 3. Square root of 16 gives me 4, so I get 7. Just a little refresher there. Let's move on. And so here we have the definition of the principal nth root of a real number. So if a to the n equals b, with a and b real numbers and n is a positive integer, then a is an nth root of b, or a equals n to the nth root of b. If n, the index, so this little number there is called the index, is even, then a is a non-negative and b is also a non-negative. If n is odd, a and b can be any real numbers. So just like a little example on that, if we have an even index, so if I have, for example, 4, the 4th root of negative 16, this is not a real number. I cannot take the root of a number if my index is even, but I can take the root of a number if my index is odd. For example, the cube root of negative 8 is negative 2, which is real. Okay, so just a little review. If we have even indexes and a negative under the root, we're going to get an imaginary number and not a real number. If I get an odd index and a negative under my radical, I can get a real number. So finding those nth roots, if n is odd, we know the nth root of a to the n is a. If n is even, the nth root of a to the n is the absolute value of a. Okay, and so I have an example here. We can say like the cube root of a cubed is just a, and the square root of a squared is the absolute value of a. Going back to the slide right before this, where we can only have a real solution if my index here is odd. Okay, if not, I have that. So this absolute value ensures that I'm going to get a positive number. Let's move on to some examples here. We have the square root of 50. So just a refresher, we have to sometimes break these down with a factor tree. So I'm going to come up with factors of 50. So let's do 25 and 2. 25 will break down to 5 and 5. When we write our simplified answer, let's circle any pairs, the numbers that's in common. Those numbers come on the outside of the radical. Any number that doesn't have a pair stays inside the radical. Square root of 27 is 9. We'll do 9 and 3. We'll do 3 and 3. Pairs go outside the radical. Anything that doesn't have a pair stays inside the radical. I'm looking for pairs because my index is a 2. If I don't see an index, it's the square root. I know there's an index of 2. We'll do 45. So if I just focus on the 45, we'll do 9 and 5. Then I'll do 3 and 3. So I'll have 3 and a root 5. The square root of x squared, we know it's just going to be x. Going back to that property right before this, if my index and that exponent are the same, it kind of cancels out. So that will simplify to an x. And let's check out D. 125, let's break that down. 25 and 5. And then we will break down the 25 to 5 and 5. Pairs come outside. Anything that doesn't have a pair stays in. X cubed, if I break that down, 1 will be able to come out, the square root, and then 1 stays inside. Okay, so think about x, so we break down to like x squared, and then x and x. Pairs come outside. Anything that doesn't have a pair stays inside. This would be our final answer. Okay, let's keep going here. Adding and subtracting like radicals. So in order to add and subtract radicals, we need to make sure they have the same index and the same radicand. So for letter A, we have the same index, square root, and we have the same radicand, 13. So we just combine these. 7 and 6 is going to give me 13 root 13. Let's check out B. We have the same index and we have the same radicand. So we're going to do 4 plus 3. That's going to give us 7, the 5th root of 2. Notice 3, I have the same index. Can I get the same radicand? So we're going to do a factor tree and see if we can rewrite that square root of 18 and square root of 50 with the same radicand. So let's come over here. We'll have 3 square root 18. We'll break down 18. We'll get 9 and 2, 3 and 3. My pairs come in the front, so it joins that other 3 that I have already in the front of the radical. And if it doesn't have a pair, it stays inside. So I've just rewritten 3 square root 18 as a 9 square root 2. So let's see if I can rewrite square root of 50 with a radicand of 2. 5 square root 50 will break down to 25 and 2, 5 and 5. That's good. If it has a pair, we'll get it in the front with joining it with that other 5 that's already in the front of our radical. And if it doesn't have a pair, it stays inside. So I'm going to be left with 25 root 2. And now we can add those. So we'll have 34 square root 2. Okay. So just because it doesn't look like they have the same radicand, we still might be able to break down using a factor tree and get them to have the same radicand. And then let's check out D. So we'll, this is our first one we're going to break down. Notice it's not a square root, it's a cube root. So this does change how we do the factor tree a little bit, but not a lot. You'll still be able to do it. 54, let's break that down. Let's do 2 and 27. And then I'll do 9 and 3, and then 3 and 3. So instead of looking for pairs when it was a square root, now it's a cube root, I'm going to look for triples. So I have triple 3s here. They're going to come on the outside of the radical. And that 2 that doesn't have a triple, we're going to keep it inside the cube root. The x will not be able to come out of the radical because there's only one of them. Cube root of y cubed, though, is just going to be y. And now let's check out this other one, 128. Let's break down 128. Let's do 2 and 64. Then let's do 4 and 16, and then 16 I know goes to 4 and 4. So I've got triple 4s here, which is good. And that 2 will stay on the inside. There's already a y in the front, and the x cannot come out. There's only one of those x's, which I cannot take out if it's a cube root. Notice now I have the same index, and I have the same radicand, so I can subtract these. 3y minus 4y is going to give me negative y cube root of 2x. Lots of steps there, simplifying those radicals. Let's move on here. This is a review of the product and quotient rules for nth roots. So notice if I have the nth root of a times b, we can separate that and have the nth root of a times the nth root of b. And then same thing for division, which I showed you in the very beginning. If we have the nth root of a over b, we can separate that and do the nth root of a over the nth root of b. This also goes the other way around. So if you see something like this, we can turn it into the nth root of a over b. And if you see something like this, we can turn it into the nth root of a times b. Okay, so let's check out a here. We have the square root of 10x times the square root of 8x. Square root of 10x doesn't break down at all. So that's why my first step is going to be using this product rule and combining these. And I'm going to get the square root of 80x squared. 10 times 8, 80, x times x, x squared. And now we can break down 80, right? If I come over to the side here, let's do 8 and 10. And I'll get 4 and 2, 5 and 2, 2 and 2. So I've got 2 and 2. Those numbers are going to come in the front. So 2 times 2 gives me 4. And then the root 5 stays inside. And then notice I have the square root of x squared, which is going to be the absolute value of x because my index is even. And that's going to be our final answer. Let's check out B. Square root of 150 x to the fourth over square root of 3x. Not too much that I can think about doing, like square root of 3 doesn't go anywhere. So let's rewrite this as 150 x to the fourth over 3x using that quotient rule. Now when I look at this, I can do 150 over 3, right? 150 over 3 is going to be 50, and x to the fourth over x is going to be x cubed. And now if I look at this, this is way more simple for me to break down. Square root of 50, we've done that quite a few times now. That gives us 5 root 2. X cubed, so I have the square root of x cubed, one's going to come out and one's going to stay in. And there is going to be my final answer. The next topic that we're going to talk about here is rationalizing the denominator. So just like we can't have zeros in the denominator, we're not allowed to have square roots in the denominator. It's bad math to have square roots in the denominator. So we do something called rationalizing the denominator. And rationalizing the denominator gets the square root out of the denominator, okay? We're just rewriting this. We're not simplifying this. We're not changing the value. We're just rewriting that. And how we do this is by multiplying by the denominator. So if I multiply the numerator and the denominator by square root 5, I'm going to get 3 square root 5 over square root 25, which is going to be the numerator is going to be 3 square root 5. Square root 25, we know is 5. Notice that will always happen. Square root 5 times square root 5 is just 5. Square root of 100 times square root of 100 is 100. And this is going to be my final answer. We love it way more because there's no radical in the denominator, and we can have radicals in the numerator. A little bit more complicated version of this is if I have a polynomial, 2 terms in the denominator. We still have to rationalize it. We're not allowed to have the radicals in the denominator. So we do this by multiplying it by the conjugate of the denominator. The conjugate of a binomial is the same terms, just the different sign. So we're going to multiply this by the same terms, but now just a different sign between them, okay? And so the numerator there will distribute 35 plus 7 root 3. And then my denominator, we are going to multiply these two binomials by FOILing. So we're going to do 5 times 5, 25. 5 times square root 3. 5 times negative square root 3. And negative square root 3 times square root 3 gives us negative 3. Notice these terms cancel, which is what we want. Notice the radicals are gone from the denominator, and we'll be left with 35 plus 7 root 3 over 25 minus 3 gives me 22. And that's my final answer. No square roots, no radicals in the denominator. This page talks about the property of if I have a fraction in my exponent. And so what we want to remember is this rule that when I have a fraction in my exponent, I can rewrite that as a radical. And so what happens is the denominator becomes the index, and the numerator becomes the exponent. Here the numerator is 1, so we don't need to write the exponent of 1. And so that is the switch that we need to do to go from radical form to exponential form. And this also applies to if I have a negative exponent. Remember, if I have a negative exponent, we rewrite this as a fraction. So this would become 1 over the nth root of a. Let's check out some examples of this. So 25 to the 1/2, I know that's the same thing as the square root of 25. So that's 5. B, I have -8 to the 1/3. I know that's the same thing as the cube root of -8. Notice I move the denominator to the index, and the numerator is the exponent, and that gives me -2. 27 to the 1/3. Oh, actually, I think this is 27 to the -1/3. So I'm going to rewrite this as 1 over 27 to the 1/3. And then I'm going to do 1 over the cube root of 27. And I know the cube root of 27 is 3. So I have 1/3. The other, it's very similar. This next page, it now just happens to show us if that exponent, the numerator, is not a 1. So here, if it's not a 1, if it's a variable, m, any number, it becomes the exponent. Okay, we can still handle it if that exponent is negative. Let's check out, here's a good visual. The numerator becomes the exponent, the denominator becomes the index. And then let's check out these examples on our last page. So 27 to the 2 over to the 2/3. Let's write this as the cube root of 27 squared. Notice off the top of my head, I don't know 27 squared, but I do know the cube root of 27. So I can do the cube root of 27, that gives me 3, and that squared is still there. So I have 3 squared, that's going to give me 9. Then I have 5x to the 1/2 times 7x to the 3/4. So first thing I see is I can multiply my numbers. 5 times 7 is going to give me 35. X, remember when we multiply variables, your exponents add. So in order for me to add these exponents, let's get a common denominator. So 1/2 and 3/4, let's make that 2/4 plus 3/4. So then I'm going to have 35x to the 5/4. And then if I can write this as a radical, I can do 35, the index is the denominator, 4th root of x to the 5th. And then notice I can take out, if it's a 4th root and I have x to the 5th, I can take out a whole x. So I'm going to have 35, the absolute value of x, because my index is even, times the 4th root of x. 1x is still left over. Okay, and now let's check out C. We're doing some division. Right away, I see 32 over 16. That's going to give me 2. And when I divide variables, my exponents subtract. So I have 5/3 minus 3/4. Again, let's get a common denominator. So let's do 2x, let's do 12. So I'm going to get 20 over 12 minus 9 over 12. Whoops. So then I'm going to get 2x to the 11 over 12. And if I write this in a radical form, we're going to have 2 indexes, the denominator, 12th root of x to the 11. Nothing can simplify because that exponent is less than the index. And there's your final answer. Okay, lots of the objectives here to review between our exponents and our radicals. If you have any questions, let me know. Great job on taking notes in section P3. Send any questions my way. Great job, guys.